Now, before I really speak about the different types of agents and what lies around over here, let me give you some very quick definitions. So, a very common question that usually arises when you talk to people is that you taught us 250 algorithms, do you know that? Yes. Which one is the best? I don't know. You find out. So, there is probably a best refrigerator, best laptop, best computer system. However, which is the best algorithm? So, which is the best algorithm all depends upon what your problem is. And therefore, it is important to understand the characteristics or the classification of the problem before you really go upon and saying that, hey, this is the algorithm that I need. So let's look at extremely quick environment classification or problem classification. So I look at what are the different types of problem and I will classify them into types based on assumptions. So one of the most important and one of the most widely used is when you talk about, is your environment fully observable or is your environment partially observable? So let's go on the easy definition first. An environment is fully observable if it has given you, or if you know everything that is needed to make a decision. Now, technically, nothing could be fully observable, and therefore it's important to note the decision and to note the definition. So, after recording this lecture, I'll go home and, of course, you know what is the approximate way that I will be using. Is that fully observable or is that partially observable? Now, one way is you could say that, hey, it's fully observable. I am here at the first floor. I'll go down, go out of the main route, take a straight, cross the sports park, and then in a few steps, I have my home. What else could I know? What else could I need? But then it is also a partially observable problem. Do I know that in the wonderful city of Delhi, there is a road that I'm not aware of? Maybe if I go to that road, it's be an awesome way to get to my home. So maybe that wonderful road that I'm talking about has the best street food, and I just love that. So now is that fully observable or partially observable because I don't know about that road? The answer is that you'll say it's still fully observable practically. Now, practically me going to Delhi, New York, Los Angeles, moon, all the stars is negligible. I don't have information about them, neither is that important. So we only talk about information that is relevant. Is all relevant information available to me? And the answer is yes. All relevant information is available to me. Now you may also argue that while going out, I may just get Professor Nandi on the way, and of course I'll have to steer around him, probably have an interaction that'll cost me some time. Now is that fully observable or partially observable? Because Professor Nandi does affect my route. Sometimes I actually have to walk with him all the way up to the office back. And the answer is a matter of modeling. We use the term well-known abstraction. So every problem will be solved at a particular level of detail, at a particular level of abstraction. If I'm just planning a generic route that satellite navigation Google Map does, I'm okay with that. At that abstraction, it's fully observable. Of course, there is a possibility that a road might be completely blocked. I'll be practical. So it's not something which is very practical to happen, and therefore I'll say at the abstraction of route planning, it's fully observable. However, imagine there's a robot, the robot sees Professor Nandi in front, it did not know when it was traveling, now it needs to adjust. At that level of abstraction, yes, the problem of initially planning the route is partially observable. So, all the examples could be taken up in exactly the same manner. So, you want to discuss something interesting with your mom, you don't know where the mom is, partially observable. You know where she is, you don't know if the furniture has moved, practically at that level of abstraction, fully observable. You're making in a nice robot that travels warehouses to deliver the order. If you just need to go from one place to the other, as a generic route, fully observable. If you want to say somebody just comes in front and you want to avoid, partially observable. You did not initially know that. If you're making in a chatbot and you just say, hey, I'm fed up of my home, I want to come to IIIT Allahabad and have delicious, wonderful mess food. So all that you tell to your favorite chatbot is book me one ticket for tomorrow, partially observable. From where to where? Of course, your biological details might be there with the chatbot, but the others, it's not there. So that's what we say for fully versus partially observable. If you are thinking, why is there non-observable? That would be a wonderful question. Non-observable. You have no information. Now, can you make a computer program, a real-life one, which does not require inputs? Not observable. You don't even know the inputs. Is it possible? I leave it for you. If you think you can come up with examples, then yes, there is a non-observable, but at least I cannot. So there's just a partially observable. You at least know the inputs. Okay, now the other thing is what we say is deterministic versus stochastic. So a system is deterministic if you exactly know what will be the outcome of the actions. I'll take a step ahead. I'll go one step ahead. Deterministic. I'll switch off this video. It's already started to pain. The video will go off. Wonderful. Deterministic. Stochastic. You do not know what are the consequences of the action. So if it was a physical class, you talk, 20% chance I catch you up and I tell you, hey guy or hey girl, that's a bad thing to do. 80% I just neglect it, which is bad. That means you're not the fanciest or the most stunning looking face of my class. I don't even pay attention to you. If you're buffering this up, whether the video will get paused because the buffering hasn't happened, or it will go seamlessly, depending upon the connection, deterministic, stochastic. Now, if you're talking about deterministic system, the easiest example to think of is the fact that you are playing a one-player game, a classic board game. So there's no roll of a dice. All you need to do is to move in a certain way. I mean, all the games of Brain Vita and all those classic games, deterministic. You know, if you take an action, what will happen? You know exactly what will happen. Stochastic, the modern day games, all the FIFAs and all the NFS and whatever is the popular game, you really do not know what will happen when you press a key. There's some kind of an uncertainty which is associated. Sometimes you move 5 meters, sometimes you move 4.9 meters, sometimes you move 4.8 meter. Now, of course, whenever I take the term stochastic, if you don't answer that in assessments, it's really embarrassing. It is nothing but probabilistic. So please don't say that you do not know what is stochastic. The teacher went very fast. You know what is the systems which are stochastic. Now, here also basically two categories have come up in the modern sense, and that's because when people like me will work, we'll say that, okay, we'll work on stochastic system, but we'll make in wonderful algorithms for stochastic system, but the input to those systems will be a probability distribution function. So if I take the action up, if I press the forward key, what is the probability that I will move exactly 4.5 meter? If the game was actually coded in a stochastic manner, the developer may give me and I may have it. However, sometimes I may not have that. So, do I have the probability distribution? And that gives rise to something which is called as non-determinism. You know it's stochastic, there's some probability. Unfortunately, you do not know the probability. Again, I'll say, can you guess the probability? So for robots, also the same thing happens. If you move at a speed of 5 meters per second, which by the way is too high, so let's make it 10 centimeters a second. You move for 3 seconds, somebody will shout out 30 centimeters. That's not how it happens. How much it moves is a function of how much friction does it place. Does it slip? Does it observe a sudden leak of the battery? Do the wheels get a little bit tilted? So there are so many things which come into play. Do I know the probability or not? That will decide whether it is non-deterministic or it is not the one. Okay, I'll go on with some quickly. So, episodic versus sequential. A system is episodic. So, if you want, just because you are sitting at home, if you want a cool way to remember episodic, I'll give you one. What happens in the daily soap? Episode 1, episode 2, episode 1500, they really pull it up unnecessarily. So, episodic is something where while making the action, you are not concerned about what happened before. You're not concerned about what happens in the future. All you are concerned about is what do you do immediately. So make an AI for coronavirus. What's the loop? Patient 1, patient 2, patient 3. For patient number 100, does it matter what decision you took for patient number 99? No. Does decision of patient number 100 affect decision of patient number 101? No. Every input is unique. Every decision is unique. And more generally, with very few exceptions, all classification problems are episodic in nature. Now let's look at the other wonderful decision you all are making. You've already made one, whether to watch this video lecture series or not. Sequential. Somewhere I will give you hints of how to pass the assessment. Your grades do have an effect on whether you watch it or not. So many of you do not get an opportunity to watch this wonderful set of videos because you did not pass the relevant courses. Okay, just joking, there is no one like that. So your decisions of the previous courses do affect what happens around over here. Robot moving, sequential, make one bad move and you'll have to mend your part altogether. So instead of going in forward, for some steps go sideways, everything is messed up. You need to reorient yourself. One bad decisions and all your future gets into jeopardy. So that's sequential. Chatbot trying to understand what do you want in your life, book a ticket, how? Sequential. Every question gives more information. If it's a very good chatbot, it will extract the maximum information in fewest statements. Otherwise, it will ask for too much information again and again. What you ask now, it affects all the future actions and it is affected by what did you do previously. So that is episodic versus sequential. Let's go to static versus dynamic. So static, the environment never changes. It remains as it is. Dynamic, the environment keeps changing. So same examples. I want to go home. Now I really want to go. It's turning out to be a torture at this end as well. So IIIT Allahabad will not make new roads for me. Not till I become a celebrity. IIIT Allahabad will not erect new structures for me. What's gonna change? Nothing. But then of course, if you look at it at the different abstraction, so a lot will change. So people will move in, people will move out, a lot of things will change, and therefore it could be called as a completely dynamic environment. Now, there is a term which is semi-dynamic. And remember that this term will have multiple meanings, so be very careful of the text. I usually accept every definition. So it's semi-dynamic when all the changes happening in the world are because of you. You are doing it. Semi-dynamic. So there was a road blockage. I cleared that up. I've accounted for that. The cost in clearing that has already been added up. Or it's semi-dynamic if an opponent whom you have modeled is doing that. So I know in my class, if it would have been a physical class, some people will shout. I've already accounted for that. I know exactly when they'll shout, why they'll shout. That's pre-planned. It was already there in my knowledge. Semi-dynamic. You're playing a game with your little sister, tic-tac-toe. You know exactly what the little sister will do based on what's the best for her. Or the performance measure changes. So again, the importance of performance measure. What really happened, everything is as it is. Suddenly, you want something else. So I look at Professor Nandi when traveling. Suddenly, my performance measure changes. Now I need to go to my office again to get some papers signed, which he has been avoiding for a long time. And I've got him red-handed. Now he cannot run. My performance measure has suddenly changed. So that's what we say is what is semi-dynamic. Let's go to, very quickly, discrete versus continuous. So of course you know that this is discrete and this is continuous. There are infinite elements out over here. I don't need to tell you. Exactly the same thing. Can I just press 4 arrow keys, up, down, right, left, to move my robot, to move my agent, to move my player, discrete? Or can I give it velocities, 5.6 meter per second, too large, 5.6 centimeters per second, 6.4 centimeters per second, continuous? So, are my states discrete? Are my states continuous? Are my actions discrete? Are my actions continuous? That is what differentiates the discrete versus continuous. So, talking about what you observe as well, discrete versus continuous, you say you could be anywhere in the coordinate axis system, 3.1, 4.2, 7.8, continuous. You say there are blocks, so the typical game of snakes and ladder, you could just be at one of the blocks, discrete. So your position at any point of time is one of the finite values, and because it is one of the finite values, you have nothing to choose from. A discrete set of options. So that is what is discrete versus continuous.